So welcome to Vamos this week. Our speaker, Mack from the University of Michigan. So Mack received his PhD in 1996 from the Helsinki University of Technology in Finland. And then he was a postdoc at the University of Marburg in Germany, a research associate at the Royal Institute of Technology in Sweden, and then professor at University of Marburg. Since 2016, he's been a professor at the University of Michigan in electrical and computer engineering and also in physics, where his group developed systematic quantum theory for semiconductor quantum optics, terahertz spectroscopy, and lightwave electronics. Professor Kira is a fellow of APS and Optica, and he's also a Marie Curie fellow. And he's a co-author of many influential papers in the field of semiconductor quantum optics and one of the first textbooks on that topic. So without further ado, Mack, I would welcome you to Vamos, and we look forward to your talk.
Hey, thank you, Mike, very much for your very nice introduction. So it's, of course, a pleasure to be here. Actually, to be honest, I'm a theorist, so I am able to work with both semiconductors and atoms. So in principle, I could have given also an atomic work. So we have been using our many-body theory, for example, to study strongly interacting Bose gases, which would have been closer to home most of you. However, I thought that it might be nicer to present things what most of us in my group are working on, and its connection to lots of things what are happening in AMO. So so here in the first page, I have listed my current group, and most of the work what I present here is done by Markus Borsch and also Wade Wu. So as mentioned, I'm a theorist, but I work very closely with experimentalists. So experiments are done in Rupert Huber's group in Regensburg, and I show also one example done together with Mark Sherwin. And in Marburg, I, of course, had lots of collaborations, so many of these things started with Stefan Koch. Okay, so let's get started. So I thought that maybe it's a good idea to illustrate why it's important to study quantum physics with solids. So obviously, it's obvious choice to look at quantum physics is to use simplified systems, so atomic and so on, because they are so much easier to handle and so it's more or less mandatory that we go that direction. There are a couple of big things that are happening right now. So you all know that information technology runs on silicon platforms or other semiconductor based, depending on if you have photonic components in them. And now if we follow how much energy they are currently consuming, so in 10 years, from 2010 to 20, the consumption has grown from 5 to 7% of the world's energy consumption, and the prediction is that in 2030 it's already more than 20%. And obviously, if that growth rate grows, semiconductors are going to swallow up most of the energy that is produced, and this is not sustainable. So then obviously the other direction, so how we combat this energy use is to make semiconductor devices smaller. And here is typical CMOS component size from 2010 to now, roughly now, and in 10 years. So 10 years back, it was 32 nanometers. Now it's about 5 nanometers. It's actually a little bit smaller than that. And the prediction is that we are in 10 years reaching 1 nanometer. And 1 nanometer, you all know that it's getting atomic. So basically, it cannot shrink anymore. And this is not going to be then the route in to make semiconductors and quantum classical information technology more efficient. And the way to go beyond it is really to start thinking in terms of quantum science and technology. So don't necessarily pack information in terms of physical qubits, but use interlace information in entanglement, space of entanglement, or space, essentially in Hilbert space. So that's kind of the thing. And obviously, I mean, this is very familiar to you. Many of you are already using entanglement between atomic ensembles and so on. So we are definitely trying to follow you in semiconductors. And the vision, just to get some numbers where semiconductors are and could be, I made a back of an envelope calculation for some critical issues there. So you do know that in condensed matter, your electrons are extremely packed. And if you run any electronic device at room temperature, the electrons scatter really a lot. And typical scattering time will be of the order of 100 femtosecond. So every 100 femtosecond you have a collision. So essentially you lose the quantum coherence every 100 femtosecond. And if you translate that one into 1 gigahertz electronics, so computers are roughly running in that clock speed, you will get 10,000 collisions within it. So it's obviously completely hopeless to get any quantum information after 10,000 collisions. So it simply doesn't work. So in order to speed it up, the electronic processes, we should obviously go to much faster oscillation cycles. And one possibility is to use oscillation cycles of the light field. So each time you're oscillating, electromagnetic field changes in sign, it could basically flip your electronic gadget. And if you take different wavelength light sources, you can reach somewhere between 1 and 5 femtosecond oscillation cycles. And compared now with the 100 femtosecond scattering time, we could get up to 20 to 100 coherent operations. So that would be pretty neat if we would be there. So if you could use light waves, the oscillation cycle somehow to drive electronic quantum information. So this is really the idea of the light wave electronics in solids. So essentially use intense carrier wave or intense light pulses to drive your electronic coherence, essentially beat the coherence, get access to the quantum coherent effects, control the flow of electrons and their many-body interactions in the quantum realm. So this would be essentially the route to million times faster electronics, petahertz electronics, and this is the way to get it operating with quantum information. So the vision could be looking something like this. So you would have a light source that, I mean, light can be already entangled, so you could use or made quantum, and you could use that one to drive and excite your semiconductor system and generate different electronic correlations there. And then you can use these light waves to switch them. And you switch them now much faster than decoherence, and then it would operate already in the room temperature. So, and when you do the switching, you are doing actually quantum information processing with multi-electron states. So it's a many-body Hilbert space where you have packed the information. And obviously, when you have these switching events, remember that we want to switch them roughly on the time scale of 1 femtosecond or so, a few femtoseconds. So obviously the sequences should be timed pretty precisely in order to do that. So we would need attosecond clocking, so or at least few hundred or to 10 attosecond clocking precision in order to make reasonable sequences. And once things have evolved, your semiconductor excitations, they might emit their information or you extract them somehow. So you obviously need some specific quantum output and detection. Obviously, this is not yet happening, so we are pretty far for it, but I'm today going to review a couple of aspects. So these attosecond clocking, how can you clock these? How can you switch information really fast? And what kind of information can you read out? So those are some of the key elements, but obviously, these are just the first steps in order to realize quantum information processing. So any questions from the introductory part, so I'm going to go a little bit to theory. So if anybody has questions, I can easily answer these.
No questions yet.
Oh, okay, good. So I will have these parts, so you can of course interrupt me anytime. So I will have 4 parts. We can go to details anytime. Okay, so I'm a theorist, so I always want to show a little bit of theory. I'm not going to be too heavy. It's Friday and it's late, so it's better to keep it somewhat high level, just to get you the key ideas rather than going to the key details. But my group is using systematic many-body theory called quantum dynamical cluster expansion. In AMO, you might know coupled clusters approach, so it's relative to that, but applied to electronic quantum fields and so on. And we are looking at dynamics, not ground states and these kind of stuff. But anyway, so we start from very fundamental Hamiltonians, which include essentially the electronic bands, the key light-matter interactions, the key electron-electron interactions, lattice vibrations, and at the electronic level. And we don't do any dephasing approximation. We actually compute how they evolve. And the evolution looks schematically like this. So you have a light pulse that comes and excites you, lots and lots of electrons and electronic vacancies, which we call holes. These are charged particles, so they interact, they might cluster together to different entities. Here, the pairs would be called excitons, triplets would be called trions, quadruplets would be called biexcitons, and so on. And the interesting part is that you can make a really rigorous analysis both for AMO systems, so we have done it for strongly interacting DCs, and also for semiconductors. The many-body dynamics is exactly the same. So if you write a quantum kinetic equation for a given cluster, it couples to all the lower order clusters, like here, and then you have the hierarchical problem, and hierarchical coupling to higher order ones. So in principle, this runs to infinity. So you might think that this is a major pain in the neck. Well, it is, but it's solvable. So the point is that if you come with an excitation which starts from plasma, the higher order clusters are created sequentially. So this term, for example, doesn't exist before a certain time. So you can formally truncate these quantum kinetics exactly at the given level and then follow how these things evolve. And if there's a dephasing process that kills the coherence and so on. So it's a really, really efficient way to solve non-perturbative excitations until the next cluster is formed. So in principle, it's a very nice way of looking at these light wave electronic things, because you typically want to encode some quantum information, then follow how that propagates. And when the next cluster grows, it's essentially terminates the evolution which you were wanting, and you can from here also learn how the decoherence works and maybe find ways to mitigate decoherence in a many-body system. So again, here is roughly how structurally the dynamics looks like. And those of you who know light wave electronics, so you get harmonics from it. So if you drive things more hard, and that comes already at the lowest level. So if you know your self-consistent single body, single particle cluster dynamics, you get the harmonics, Rabi flops, Bloch oscillations. You can also describe ultra-strong coupling effects. Coupling to the next body will give you dephasing, relaxation, and so on. So if you store your quantum information here, that would be the leak. But on the other hand, if you are able to read this two-body thing, you might actually still revive your quantum information if you are able to measure correlations. And this goes on, and depending on your application, you have to treat problems to different levels. And just to give you a flavor, so the single body dynamics, essentially in a semiconductor, you have a conduction band and valence band. It involves polarization and densities. and the polarization is driven by the light field. And once it's created, it will be also translated by light field, and semiconductors will have also geometrical effects via the curvature and so on. The new important thing, or anybody think what is important, are the Coulombic renormalization. So you won't see the bare in the bare states, but you see also bound state resonances like excitons and so on. And you do have the coupling, and the coupling schematically looks like that the polarization scatters with an existing electronic occupations, and it looks like Boltzmann type, but it's more complicated than that. And it will bring you essentially screening to your interactions, excitation-induced dephasings, also can generate the next cluster. It will also introduce quantum memory, so the scattering depends on polarization at the earlier time. So this is kind of the toolkit what we are using, and I will next start discussing how I use it for attosecond timing. So this might be a next good break. So if anybody had some questions about the theoretical aspects.
Yeah, sure. So in your cartoon, like the first step is always the encoding of the quantum information at the base level. So can you give an example of how quantum information would be encoded within this type of scheme?
So, okay, maybe actually show these pictures. So in the lowest level, what we want to do, we quite often use just classical lasers. And now in a semiconductor, in a band structure, I will show actually an example. You can target some specific regions of the band structure. And there you can, for example, excite excitations with a certain spin. And when you do that, you could use that spin as a kind of a qubit relevant information. And then you ask how much is that polarization coherence living, and as long as it lives, you can then, for example, flip it and these kind of things.
I see. All right, thank you.
Okay, good. Let me move to the attosecond timing. So that's the theoretical gearwork what we are going to use. And I did mention it that now if we want to do this flipping of quantum information, timing is pretty important. So now I did mention it as a goal that we should try to get to the attosecond timing. And of course, the first challenge is the Heisenberg limit. So if you just make a quick back of an envelope calculation, 1 picosecond time resolution means that if you come with a 1 pulse, you can measure things with 4 milli-electron volt resolution. And if you go to 1 attoseconds, it's already 4,000 electron volts. And this is obviously a problem because attosecond pulses, if they have kilo electron volt energies, electronic transitions are electron volts, quite often even less, so milli-electron volts also. So it doesn't work for single pulse very well. However, you can do obviously a different thing. So you can have 2 pulses, 1 reference pulse, and then, for example, harmonic emission. And you can easily, well, not easily, but in principle, time 2 events. So, for example, the peak of your terahertz, peak of your driving field, and peak of your emission, that you could, in principle, time way more accurate in a sub-cycle resolution compared to the oscillation. So Heisenberg uncertainty is obviously related to the single pulse resolution, which is defined by the cycle, whereas here it's just a question of how accurately we can measure 2 events peaking. And the things actually, when you are looking at non-perturbative processes like harmonics, they will be very sharply peaked. So it will be relatively easy to get massively sub-cycle resolution. So And that's kind of the route to attosecond also here in solids. So you can measure milli-electron volt scale effects if you are able to measure it against a reference. So our workhorse is harmonic sideband generation, and let me now walk through. So that's a little bit different than high harmonic generation. It really needs two pulses. So the red pulse here is the one that is resonant with the band-to-band transitions that creates you the coherencies, what you need. And then you have another pulse, this blue, slower pulse, that typically is terahertz field or let's say multi-terahertz field. And what it does, it's completely non-resonant to the, so it will have some tens of or hundreds of milli-electron volt energies. The band gap is of the order 1 to 2 eV. So it's a couple orders of magnitude less energetic but on a photon level. So what it does, it cannot make intra-band transitions, but what it does, once you have generated here coherencies, it can move them back and forth. And the key process is actually to typically excite coherent excitons. And they will be electron hole pairs that are bound, and then you come with a terahertz field which separates them and then recollides them. And this part is equivalent to the AMO three-step model in high harmonic generation, where you also ionize the electron, accelerate it, recollide it with an ion, and you get harmonics. So, and the first demonstration, or one of the first demonstration, was about in solids, was about 10 years back. So Mark Shervin's group showed with a free electron laser. This largest peak here is the typical excitonic resonance, and you see multiple peaks. They are offset by the harmonics corresponding to terahertz frequency. This is of course nice, and but with a free electron laser, you have not the time resolution to see the collision. So we did a couple of years later with a faster pulse and a different material. So tungsten diselenide bulk. We had 100 femtosecond optical pulse. It's quite a bit shorter than the free electron laser, so there's some time resolution. And then we still saw the nice side bands, and we could actually time the emission compared to the terahertz driving. And with that one, we could verify that the recollisions are happening there. So this is a theory version of it. So let's have a look at the guts, what's happening there. So that's shaded area. Okay, I'm showing temporal evolution of different entities. So shaded area is the terahertz driving. I've taken absolute value, so it should go down, but just to highlight what's going on. Here, the dashed line is the near infrared excitation, so that creates the coherencies. And now what I'm following here is a red line and a blue line are the polarizations corresponding to harmonics. So I basically filter the emission so that I remove the primary emission. I only look at the harmonics. And you do see that it is delayed and it peaks at some time. And here I've made two calculations, one with monolayer and one with a bulk tungsten diselenide. And the difference is that the monolayer has way much higher Coulomb interaction or Coulomb attraction than the bulk. And you see there's a difference of the delay. But that's not the point what I wanted to make here in the picture. But in the calculations, what we can monitor is the Wigner function of my coherent excitation. So actually it starts from here in the zero at origin, and now the electron hole pairs will be displaced. So it makes this kind of curved, and this orange path shows the path just before the recollision. So x-axis is displacement. So when it's zero, you have recollided, and lo and behold, the polarization at the moment, when it's maximized, I do see a recollision. So the wave packet has returned back to the origin. So this was very nice. Another interesting part, what you see that there's a difference here. and between the monolayer and bulk, and this is easily understandable via the interaction. So you do understand that when you have strong interactions, the electron and holes are, so the field tries to drive them apart, but the interactions are trying to bring them closer. So with a stronger interaction, you make a smaller loop and you collide faster. So there is a delay difference. And this is the key delay what we are starting to measure. So let me recap. So that's a driving field. Now this one is kind of a classical case-based or phase-based coordinate. So for monolayer, if the excitation starts from here, it goes, the electron and hole pairs are separated, then they come back, and that's the recollision. That's the time when you get most of the harmonic sideband emission. And if you compare it with a no Coulomb interaction, you get much longer trajectories. And if you would like to get to the same point, same amount of evolution, you actually have to delay the classical thing. So simply because, so there's a couple of factors. So coherence will live certain time. So if you want to have the same time of the time of flight, you have to delay the weaker interaction more, simply to have this to have less action by the field. And the interesting part is that the time of flight, combination of time of flight and this excess energy will regulate how strong the emission is. So we will see modulation in the emission, and the time delay between the terahertz emission, terahertz excitation, optical excitation will dictate when there is an optimal emission condition, and we call it that will allow us to auto-clock these two events. And here are the actual measurements. So have a look at it. So here, that's the terahertz driving field. Now this time I haven't taken absolute values. Here is how the terahertz, some harmonic sideband intensity behaves. So you do see that they are pretty much synchronized with the field crests, but they are slightly delayed. So these are the delays. And now I have comparison between a monolayer, it has a 300 MeV binding and exciton binding energy, versus bulk 60 MeV binding energy. So Coulomb interaction in a monolayer are about 5 times stronger than in a bulk. And if you look at closer, you do see these delays. So the paths are longer, tend to be longer in the bulk. So in order to have the same flight of time, I have to delay it further from the crest. So, and Rupert Huber's group did enormous job to stabilize everything, and they could, at the end of the day, measure these delays with about 300 attosecond resolution. And the dots here are measurements, and the shaded areas are our quantum dynamic cluster expansion calculations. So we can quantitatively get them, and here you see that the delay is roughly of the order of 1 femtosecond, and with the 300 femtosecond accuracy. And I want to point out, compared to the terahertz cycle, we are about 0.7 millicycle accurate. So this is pretty dramatic. So, and this is the way we can access things in a solid, also with an attosecond resolution. Let me little bit look to the guts. So here on the left, I've plot actual spectra as function of the excitation time. And you again see the modulation, good excitation times bad, good, bad, good, bad, and so on. And you remember that this is now delayed with respect to the terahertz field. So that's our calculation. And this is experiment, and these are done now in the same absolute unit. So you do see that the agreement is pretty remarkable. But it's not only that why I wanted to point it out, but this will allows us to then go to the theory and start switching on and off certain contributions. And now we actually looked to the really key event, that's the dephasing. So in the red line here in the right, so this one shows the sideband spectrum. The fundamental is somewhere here, so it's cut to the tails. So that's the interesting part. So the red, of course, agrees with the experiment in detail, but then we can try to make a simplistic model. So the red will include everything, so microscopic scattering and everything. These ones are phenomenological dephasing. So in case I want to get the magnitude right, I have to use relatively long lifetimes for coherence, and then you see all kinds of oscillations which are not there, so that doesn't work. On the other hand, if I want to get similar level of oscillations, I have to go to much shorter time scales, but then the magnitudes get completely wrong. And this is a signature actually that the coherence times changes during the excitation, and the only way to include it is so you cannot do it with a single dephasing constant. You really have to compute it microscopically if you want to get quantitative understanding. So that's kind of the message here. Okay, that was the bit for the theorists, but now why are we so excited about attosecond timing? So this is a means to actually detect correlations directly in these different quantum materials. So tungsten diselenide monolayer is one of the 2D materials which are heavily studied right now. And what we wanted to look at next is that we can moderate the strength of the Coulomb interaction in semiconductor simply by exciting it differently. And here is how many electron hole pairs we excite. The more you excite, the stronger the screening is. And the theory predicts that the delay will increase simply because you are decreasing the interactions. And the experiments did corroborate that one. So this is really exciting. Then on top of it, we started looking at cases where there's a phase transition happening. So what transition essentially? So you have excitonic insulator. So you have bound excitons here, and then you have plasma on that side. And essentially that changes. So when you go from excitons to plasma, what happens is that the electron hole pairs are first strongly Coulomb bound and then almost not bound at all. And what we found here is that this kind of a cusp. So we are still trying to figure out what happens in this cusp, but obviously we got really excited that this would be a perfect way of seeing phase transitions in condensed matter. Okay, good. So maybe some attosecond questions. I think the other parts will be shorter, so I think we can have a chat.
All right, yeah, so we've got two related questions to start with. So the first question comes from Dmitry Budker, and the question is, does it matter that spectral selectivity is completely lost with short pulses? And the second question, which is related, says, how can you actually address specific parts of the band structure? So I wonder if you could talk a little bit about how this the sideband generation maintains both excellent time resolution, but also spectral selectivity in the excitation.
Okay, yep. So yeah, that's completely right. So there's always a price to pay. If you want to time things, then you do see that the harmonic sidebands, so these are not very clear, right? So I mean, you might see here something, and this one also implies that you have some fuzziness in the if you want to map certain regions in the electronic space. I'm actually going to show you next when you make this pulse excitation pulse longer. So instead of using 10 femtosecond pulses, we are going to use roughly 100 femtosecond pulses. These peaks comes really narrow, and with that one, we'll be able to actually resolve the energetics. So we haven't really looked at completely what, I mean, it's clear that if you make pulses shorter, you lose energy resolution, but there's always some gray zone where you can have maybe both simultaneously, not of course to the optimal, but at least partially.
All right, the second question says you showed the difference between your model and the simple time constant decoherence is quite significant. So what is the nature of the decoherence in the model, and can you explain more about how this is related to the notion of quantum memory?
Okay, yeah. So there are two aspects. So when the excitonic coherences are moved, so initially they are actually 1s exciton-like, but once you start to move them far away from the high symmetry points, they will become higher excitonic states. And in a semiconductor, the dephasing is quite different than in AMO. So it's very strongly state dependent. So exciton has much longer lifetime than the higher excited exciton states. So that's one aspect. Then another aspect is that these collisions, dephasing is driven by Coulombic or phononic collisions, and it will take time before they are built up. So essentially the Heisenberg uncertainty, they are never instantaneous. So what they will be always moments. So in the early times, the dephasing is almost non-existent, it builds up, and then later time it's stronger. So these two aspects are in these ultra fast or actually at femtosecond scale excitations, they have an interplay, and they are not mappable by a single dephasing constant.
All right, thank you. I think you can continue.
Okay. Good. So I'll do very quickly. I mean, this one is now maybe related to the how I single out excitations in a semiconductor. Now I'm going to use slightly longer pulses. Well, actually, not here. I'm actually using relatively short pulses, but here I'm now going to discuss the Valetronic excitation. So this is a typical 2D material band structure. So what they have typically two special points, K and K prime. And what's different here is the sigma plus excitation excites the K valley, sigma minus the K prime valley. So the idea of Valetronic qubit is that you use one of the polarizations to generate just polarization to one valley, and then you come with a very strong pulse and move it to another, and that's your basic flip operation. So how well is that working? So let's have a quick look at it. And this is a calculation. So this is picture. We are using 10 femtosecond. Well, hold on. I think this one is okay. There it is. 5 femtosecond pulse in calculation, 10 femtosecond in measurement. So that's how the polarization looks like. So here you see the level of selectivity. Yes, it's selective, at least that it's not in the K prime valley, but it's pretty broad on all that. And then in about 5 femtoseconds with a strong enough field, you can move it there. And this is actually verified in an experiment. A little bit longer pulse, as I mentioned, 10 femtosecond, and not completely optimized terahertz pulse. So we got 66% transport. So what happened here is that initial polarization, circularly polarized here, became elliptic after the excitation for the harmonic. So yeah, so interesting part is that we can flip stuff very fast. So let me then answer this is also actually a nice question about how do I read out things more precisely. So now we are going to use longer pulses, again, similar band structure. And here in the false color, you see the coherencies slush back and forth. And let me simplify the motion just a little bit. So classically, you could think that you create the coherence here as a wave packet, and then you move it. It follows the terahertz pulse, okay? So roughly sinusoidal. When you think it as a sinusoidal one, what does happen is that when it gains energy here, and when it comes back, it releases the energy. But from a district point, if you want to know at which energies corresponds to which K distribution. You just take a Fourier transformation of your polarization distribution as a function of time. And here, this number obviously tells you which harmonic you are monitoring. And now if you stare this one a little while and you realize that if you are sitting here, if you pick a K value and figure out how the Fourier transformation works, during one cycle, it crosses one K point twice. And obviously the crossing points vary as function of K. And you will get essentially two bursts from a Fourier transformation is consisting of two bursts of polarizations, and they add up together to give you interference pattern. And the interference pattern is like adding two spectra together, so you will get frequency like structure. And indeed, if you do that here on the screen, depending on which I look at this motion from the point of view of different harmonics, I will see one peak, two peaks, three peaks, and so on, depending on which harmonic I'm going to look at. And we call these crystal momentum combs because these are combs in K space. So why are they interesting? So, okay, here is the actual polarization dynamic. So it does look roughly sinusoidal, has some structure, but this argument for frequency combs or K combs what I gave, it still is there, because you see that every time I go make a cross section, the major peak passes it through twice, and each harmonic will perceive a different frequency comb, a crystal momentum comb. So now the position of the outermost one can be more or less constructed classically. So it's roughly the classical K motion so if you replace that by sinusoidal one, you know what that K position is supposed to be. But obviously these distortions will moderate it. So you have many body corrections. We can compute it, and we find it that it's roughly between 0.5 and 1.5, depending on case. But anyway, that's what it is. Now you have, that's roughly the maximum excursion of the wave packet. Then the COM is defined by number of nodes. So it's the maximum excursion divided by the number of nodes plus 1. So the outermost COM here, or the outermost peak, which we call as a K-COM, has a width that decreases with n, so we can get much smaller resolution than the excursion area it has passed. And then another interesting feature, what we learned, is that the harmonic sideband emission onsets when this crystal momentum combs passes the energy of the band. And the point is that the harmonic energy is fixed. We know for each excitation where the K is. So if that one passes the band structure, it starts to, the harmonic starts to increase. So when you are below energetically this point, there is very little emission. And with this simple idea, what we did, we actually scanned tomographically field strength, which controls the K, how large is the K, and then the frequency. So we could go through a large phase space of harmonic excitations and compare it against the electronic band structure. And indeed, you could really clearly detect edges here every time the comb line passed the band structure. And now, in order to verify that this is really reality, Rupert Huber's group did make a heroic experiments running stabilizing pulses with respect to frequencies, intensities, and swept both of them to some specific regions. And these crosses here are from experiment scaled only at one point, and all the others are then in the same color and we were amazed. You can see that it's almost looked like that we just have made boxes, but it's a different color scheme. So essentially what it tells us that yes, our interpretation was correct. So the K-combs really identify the edges of the band structures enormously closely, and we did make them some pattern recognition. So essentially figured out with essentially gradients. So whenever this gradient was large, we constructed a thing. And yes, indeed, you can have all optical band structure construction coming out of these. Of course, you need, in order to have such nice figure, you need many-body calculation to compute the exact position of the K-comb. We asked whether or not can you do it without it, and we did the same. You used the same data and just used one constant for all cases. So you do get roughly the band structure. You at least see whether or not you have bands in the regions where you are looking at, but you get obviously some aberrations. So the C is a little bit non-trivial, but it's pretty okay, at least for diagnostic purposes. Okay, before I wrap up, so if are there right now questions, I can then maybe wrap up.
I think you can wrap up and we can ask questions at the end.
Okay, good. So let me return to the vision picture. So now I've shown a couple of examples where the lightwave attosecond, or let's say lightwave electronics is in solids. So we can time excitation events with millicycle resolution. So currently 300 attoseconds. So it's for semiconductors or solids. This is really something. And the nice thing about it that resolution is sufficient to see interest in many-body. So you can detect the correlations directly. So timing, first steps taken there. First steps are also taken to flip electronic coherences. Remember, these are room temperature measurements in a real solid, so we could flip coherences already at a 5 femtosecond time scale. And if you are going to use Valetronic degree of freedom as a qubit, essentially you have flipped a qubit from one to another. Obviously, much needs to be done in order to chain these events, but it's a start. On the detection side, we are able to measure with super resolution. You need longer pulses for the excitation, so it's not attosecond resolved to do it, but you can still measure electronic states. And I didn't show it here, but well, it's actually connected. So the flipping of the qubit can be also understood as a geometrical effect. So the orbital structure changes as you go from K to K prime value. So the orbital structure, you not only measure the harmonic intensities, but you also measure the polarization direction, and that allows you to quantify the geometrical effects. And Mark Sherwin's group has done it independent of us. So yeah, so we are making headways, lots to do, but that keeps us occupied, so that's good. And maybe as a very last thing, there are, besides my work, obviously in Michigan, we are also working in a greater scale in this quantum area. So we have a Midwest Quantum Collaboratory between Michigan State and Purdue with all kinds of topics. So if you are interested, we can come back to it. So thank you, and time for further questions.
All right, thank you for the nice talk. So right now we have one question already. So after going through the many-body Hilbert space, how do you interface the output with another quantum device?
Yeah, that's a good question. So that's an open question. We are currently okay. So there are first really simple technical questions. So the quantum for this quantum flip, the quantum efficiency is first of all quite low. So the coherence has decayed pretty low. So we are currently working on schemes how to get it. So I think currently these quantum efficiency is only few percent. We have already configurations where it's tens of percents. So you obviously want to have increase the coherence times quite a bit. And then what you can do is that you come with, so what you absorb light as upstate, you flip it to downstate. This downstate, if the quantum efficiency is large enough, it would be strong emission that you can change to next layer, and next layer. So this could be a route, no demonstrations yet. So I'm just giving you an example how it could be done. Another example is that you can have relatively small excitation spots, so one micron or so. So you can make it in an array and try to combine. So you essentially have to have circuits that include semiconductor part and optical part, and you intermix those, and they should then talk one way or another. And one direction is then to use extreme nonlinear materials, which we are also trying to develop. So things that would need only very few photons to change the nonlinearity in between these operations.
Okay, and another question comes from Austin Minich. It says, regarding the applications of lightwave electronics, can you address the limits in the number of coherent cycles for computation being relatively small? So these pulses have on the order of 10 to 20 coherent cycles?
Yeah, so it will be 10 to 20 in kind of regular systems. So, and this is room temperature. Obvious route is to go to lower temperatures, then you can increase them to hundreds. Then the other route is what's really exciting is that in this collaboratory and generally in the world, there are lots of the material development, material science is making huge leaps of progress. So we find new and new materials. So our colleagues are, for example, working in these topological materials. There, the coherence times are way longer. So that's an alternative thing. So these are currently just the test beds, just to show the ideas. When the rubber hits the road, we really have to start really ask these. I think these are exactly the question. So I want to have certain coherence times. What is my tool material which I have to choose?
Mm-hmm. All right, there's one more question coming in. So similar to the issue with materials, what about using nanostructures or microstructures?
Yes, absolutely. So I did mention these extreme nonlinear materials. So one thing to amplify the light matter interaction is to use nanostructures and so on. So that's absolutely necessary once you really start engineering these things. So then nanostructures in other sense. So we are working on, for example, having these 2D materials, positioning the really tiny micro disks. So these are heterostructures that are you can put two monolayers, two different monolayers, and then you can, for example, have more qubit-like features. So essentially quantum dot typic like yeah. So there are lots of possibilities. Your nanostructure, the electronics, your nanostructure to get the light confinement or light matter interaction. So there are lots of things that you can do, but obviously everything is extremely challenging. And I maybe should say, so for the TMDs currently, the major challenge is the material quality. So we can show stuff for individual, so it's very hard to have two spots that are identical, for example. So these can be a cursing and a curse or the blessing, depending what you are doing. But usually, I mean, for scaling up things, it's a difficulty. So obviously, there has to be lots and lots of material development going in order to improve the quality. But this is true for most of the quantum science studies. So I'm not working myself with the superconducting qubits, but there they are, I think, also worried about exactly the same problems as semiconductor people. So how do you get so good quality that you can relate reliably design a quantum feature and repeat it and scale it and these kind of things?
All right, thank you. So I think that's the end of the questions that we have. So I just want to take this opportunity to once again thank you for giving such an interesting talk. Lindsay, can you let us know when is the next VAMOS talk?
It will be in 2 weeks with Andrei Derevienko, kind of giving a very interesting talk whose name I've forgotten now, but yeah, we'll see you in 2 weeks.
All right, thank you, Mack.
Yeah, thank you. Thank you for having me.
Bye.
Yeah,
Bye.
bye.